My name is Alara, and welcome to the Late Night Science Channel. Tonight, I want to tell you about something that's been painting our skies for billions of years, long before any of us were here to see it. There's this moment, when you're standing in the cold, breath turning to mist in front of you, and suddenly, the sky just opens up, not with sound, not with thunder, but with color. Waves of green and violet, ribbons of light that shouldn't exist but somehow do, moving across the darkness like they're alive. And if you stay with me tonight, if you let yourself sink into this story, I'm going to show you why these lights exist, what they really are, and maybe, by the end, you'll understand why people have been falling asleep under these skies for thousands of years, feeling somehow connected to something much, much bigger. So maybe, just maybe, hit that subscribe button if you want more of these quiet journeys into science, because honestly, there's so much more to explore together. Now, let's begin where everything begins, with the sun. See, the sun isn't just this bright ball of light sitting quietly in space. It's restless, constantly moving, churning with energy that we can't even begin to imagine. Deep in its core, hydrogen atoms are being crushed together, fusing into helium, and every single second it's converting millions of tons of matter into pure energy. That energy works its way up through layers of plasma, taking thousands of years just to reach the surface. And when it finally breaks free, it doesn't just become the light we see during the day. Some of it becomes something else, something called the solar wind. This wind isn't like the breeze you feel on your face. It's a stream, a constant stream of charged particles, electrons and protons, that flow outward from the sun in every direction. They travel through space at incredible speeds, sometimes over 1 million miles per hour, carrying with them pieces of the sun's own magnetic field. And when I say constant, I mean it. It never stops. Right now, as you're listening to this, that wind is rushing past Earth, brushing against our planet's magnetic shield. And some of those particles, some of them find their way through. Earth, you see, has this invisible shield around it. We call it the magnetosphere, and it's created by the molten iron spinning deep inside our planet's core. This motion generates a magnetic field that extends thousands of miles into space, wrapping around us like a protective bubble. Without it, the solar wind would strip away our atmosphere, slowly eroding everything that makes life possible. But instead, the magnetosphere deflects most of those particles, bending them around us, sending them streaming past into the darkness beyond. But here's where it gets interesting, and I mean truly fascinating. The shield isn't perfect. It has cracks, places near the poles where the magnetic field lines curve back down toward Earth, creating pathways, like invisible funnels, that guide some of those solar particles directly into our atmosphere. These particles spiral along those magnetic lines, bouncing back and forth between the northern and southern hemispheres, drawn inexorably toward the poles. And when they finally reach the thin upper atmosphere, about 60 to 200 miles above the ground, they collide with the atoms and molecules floating there. Each collision it's like a tiny transfer of energy. An electron from the sun strikes an oxygen atom or a nitrogen molecule, and that impact excites the atom, pushing one of its electrons into a higher energy state. But atoms don't like to stay excited. They want to return to their ground state, and when they do, they release that extra energy as light. And that light, those countless billions of collisions happening every second across hundreds of miles of sky, that's what we call the aurora. The color you see depends on which atom is glowing and how high up it's happening. Oxygen, when it's struck in the right way at the right altitude, glows green. This is the color most people think of when they imagine the northern lights. that soft, luminous green that looks almost like it shouldn't exist in nature. It happens around 60 to 150 miles up, where the air is still just thick enough for these collisions to occur frequently. Your eyes in low light are especially sensitive to this particular shade of green, which is why it's often the first color you notice when the aurora appears. But oxygen can glow red too, higher up, much higher, where the atmosphere becomes so thin that atoms can hold on to their excited state for longer, sometimes a minute or more before releasing it. Oxygen produces a deep crimson glow. This red aurora appears above the green, like a soft crown hovering at the very edge of space. It's dimmer, more diffuse, spreading across the sky like a whisper rather than a shout. Ancient people who saw these red lights sometimes thought they were seeing distant fires, flames on the horizon that never seemed to get closer. They would run to warn their neighbors, only to find nothing burning, just the sky itself wearing this strange, blood-colored veil. Nitrogen adds its own colors to the mix. When nitrogen molecules are excited, they can glow blue or purple, creating these cool, almost electric hues that often appear at the edges of auroral displays. These colors trace the faster, more energetic parts of the aurora, the places where electrons are streaming down with extra force. You'll see them as borders, as highlights that give definition to the broader curtains of green. Sometimes they form thin streaks that race across the sky, here and then gone, like someone briefly sketched them in light before erasing them again. The amazing thing is that every single photon, every tiny particle of light you see in an aurora, was created by this process. Each one represents a moment where a piece of the sun met a piece of Earth's atmosphere, and they exchanged energy in the only way they could. It's almost intimate when you think about it. The sun, 93 million miles away, reaching out across that vast emptiness, and Earth responding with color. But the aurora doesn't happen everywhere. It can't. The way Earth's magnetic field is shaped means that particles can only reach the atmosphere near the poles, creating these ring-shaped zones we call auroral ovals. One circles the north magnetic pole, the other circles the south, and they're usually centered somewhere over northern Canada, Scandinavia, Siberia in the north, and over Antarctica in the south. If you want to see the northern lights, you need to be inside that oval, or at least close enough that the aurora can arc across your horizon. These ovals aren't fixed, though. They breathe with the rhythm of solar activity. When the sun is calm, when the solar wind is gentle, the ovals shrink, pulling closer to the poles. But when a solar storm hits, when the sun releases a massive burst of energy called a coronal mass ejection, the ovals can swell dramatically. Suddenly, the aurora appears much farther south, visible from places that normally never see it. There are records from history of auroras being seen from the Caribbean, from Rome, from places where the very idea of northern lights seems impossible. But it happened, and it could happen again. The solar wind itself varies constantly. Sometimes it flows steadily, carrying the sun's magnetic field in a particular direction. Other times it becomes turbulent, twisted by storms on the solar surface. The orientation of the sun's magnetic field when it reaches Earth makes an enormous difference. If the field points south, opposite to Earth's own field, it can open up more pathways for energy to flow through. This is when the biggest auroras happen, when the magnetic fields connect and reconnect, releasing vast amounts of stored energy in sudden bursts. Scientists call these events substorms, and they're like the aurora's heartbeat. Energy builds up in Earth's magnetic tail, that long extension of our magnetic field that gets stretched out on the night side of the planet by the solar wind. It can extend past the moon's orbit, this invisible tail of magnetism, and inside it, magnetic field lines get twisted and stressed until they can't hold anymore. Then they snap, reconnecting in new configurations, and when they do, particles get flung back toward Earth, racing along the field lines toward the poles. From the ground, you see this as a sudden brightening. A quiet arc of light that's been sitting peacefully on the horizon suddenly erupts into motion. Curtains of light unfold, reaching up toward the zenith, twisting and folding over themselves. The colors intensify, greens becoming almost painfully bright, reds bleeding down from above, purples racing along the edges. The whole display can transform in seconds, going from calm to chaotic, and then, just as quickly, it begins to settle again. The substorm passes, the energy dissipates, and the aurora returns to a gentler state. If you're standing beneath one of these displays during a substorm, there are no words that quite capture it. The sky feels alive, actively moving in ways that nothing else in nature does. Clouds drift, stars wheel overhead with Earth's rotation, but the aurora dances with its own rhythm, responding to forces that are invisible and impossibly far away. You can watch a ribbon of light race from one horizon to the other in heartbeats. You can see folds and pleats form in the curtains, like fabric being gathered by invisible hands. Sometimes the aurora seems to pulse, growing brighter and dimmer in waves, as if it's breathing. The silence makes it stranger. You expect sound with movement like that, but there's nothing. The air up there is so thin that even if collisions made noise, it would never reach the ground. So you stand there in absolute quiet, maybe hearing only the wind or the crunch of snow under your feet, while overhead the sky puts on this tremendous display without a whisper. Although, and this is interesting, some people insist they've heard the aurora. Reports come from Arctic travelers, from indigenous people who've lived under these skies their whole lives, describing faint crackling sounds, like static electricity or the rustle of dry grass. For a long time, scientists dismissed this, saying it was impossible. The aurora was simply too far away. But recent research suggests that maybe, just maybe, under the right conditions, charged particles can build up near the ground during intense auroral activity, and when the field above shifts suddenly, these charges can discharge, creating tiny electrical pops that someone with sharp hearing might pick up. It's still debated, but the idea adds another layer of mystery to the whole experience. The indigenous peoples of the Arctic have their own explanations, ones that feel more complete than pure physics. The Sami people of northern Scandinavia call the lights guavsahas, which means the light you can hear. In their traditions, the aurora carried sound, whispers from another realm, and you had to treat them with respect. Speaking too loudly beneath them, or pointing or whistling, these things were considered dangerous. The lights could descend, could take you away if you weren't careful. There was reverence there, an understanding that something sacred was happening in the sky. Inuit stories speak of ancestors playing games in the heavens, kicking around a walrus skull for sport, and the aurora being the light from their torches. Or sometimes the lights were spirits of the dead, trying to communicate with the living, sending messages of guidance or warning. In Finnish mythology, the aurora was created by a fox running across the snow, its tail sweeping up snowflakes that sparkled and glowed in the sky. The Finnish word for aurora is revontulet, which literally means foxfires. These stories aren't just poetic. They represent thousands of years of human beings trying to make sense of something beautiful and mysterious, long before we had the tools to measure magnetic fields or detect solar particles. And in a way, the stories and the science aren't really contradictory. Both are attempts to understand our connection to something vast, something that links us to the cosmos. The ancestors who watched these lights didn't know about plasma physics, but they understood that the sky was communicating, that Earth and the heavens were in conversation, and they were right. The aurora appears in both hemispheres simultaneously, mirroring each other across the planet. When the northern lights are active, the southern lights, the aurora australis, are usually active too. They're connected by the same magnetic field lines, so a particle that excites atoms in the north often has a partner doing the same thing in the south. From space, satellites can see both auroral ovals at once, glowing like twin crowns around the planet's poles. But the southern lights are seen by far fewer people. Antarctica is remote, harsh, largely uninhabited except for research stations. There are no cities beneath the southern oval, no towns where people gather to watch the sky. The aurora australis shines mostly in solitude, over ice and empty ocean, witnessed by penguins and seals, and the occasional scientist brave enough to venture outside during the dark Antarctic winter. Those who do see it describe something just as magnificent as the northern displays, sometimes even more intense because the southern magnetic field is slightly stronger and more compact. The shapes the aurora takes are guided entirely by magnetic geometry. Every arc, every curtain, every ray traces the invisible structure of Earth's magnetic field. When you see a long east-west aligned arc sitting on the horizon, you're seeing the place where field lines are roughly parallel to the ground. When curtains drape down from that arc, you're seeing places where field lines dip more steeply toward Earth. And when rays shoot up, appearing to radiate from a single point overhead, you're standing directly beneath a spot where field lines point almost straight down. This last formation, called a corona, is one of the most stunning aurora configurations. It happens when you're positioned just right within the auroral oval, and suddenly all the structure seems to converge above you. Rays of light stream outward in every direction from a central point, like you're looking up through a tunnel of light. The effect is entirely perspective. The rays are actually parallel, but from where you're standing, they appear to meet, creating this explosive radial pattern. Photographers love capturing coronas, but they're even more powerful to experience in person because they create this overwhelming sense that the aurora is directly overhead, surrounding you. The aurora can form other shapes too. Sometimes you'll see these great looping structures called omega bands, shaped like the Greek letter, floating across the sky. These mark places where magnetic field lines have temporarily reconnected beneath themselves, creating closed loops of current. They drift slowly, these huge arched waves of light, and then dissolve as the magnetic configuration shifts again. They're relatively rare, and seeing one feels like witnessing something that shouldn't quite exist, too perfectly geometric to be natural, but unmistakably real. Then there are pulsating auroras, patches of light that flicker on and off in steady rhythms. These happen after substorms, when electromagnetic waves in the magnetosphere start controlling the flow of incoming electrons. The waves act like gates, periodically allowing particles through and then blocking them, and the result is this hypnotic blinking pattern in the sky. The patches can pulse for hours, beating slowly like a distant heart, and if you watch long enough, you start to feel drawn into their rhythm, your own breathing unconsciously syncing up with the flicker of light above. Sometimes the aurora appears as diffuse glows rather than structured forms. These are usually proton auroras, created when hydrogen nuclei from the sun, rather than electrons, collide with the atmosphere. Protons interact differently, producing a softer, redder glow that spreads across large areas without much definition. They're harder to see with the naked eye, often requiring instruments that detect ultraviolet light, but they're there, adding another layer to the complexity of what's happening overhead. And then there's Steve. This is a recent discovery. something that citizen scientists and aurora photographers found just by comparing their images and noticing this strange purple streak that appeared in skies much farther south than normal auroras. Scientists looked into it and realized it wasn't a typical aurora at all. STEVE stands for Strong Thermal Emission Velocity Enhancement, and it's caused by a narrow river of extremely hot plasma flowing through the upper atmosphere. The gas heats up so much, thousands of degrees, that it glows with this distinctive mauve color, completely different from the greens and reds of regular auroras. Beneath STEVE, there's sometimes a pattern called the green picket fence, rows of vertical green columns that flicker rapidly, looking like fence posts made of light. These are more traditional auroral emissions, but they're associated with the same overall phenomenon that creates STEVE. The whole thing has challenged our understanding because it appears so far from the poles and behaves differently from what we expect. It's a reminder that Earth's magnetic environment still holds surprises, still has patterns we're only beginning to recognize. The study of auroras is actually relatively young as sciences go. For most of human history, we could only watch and wonder. The breakthrough came in the early 20th century when scientists began to understand the connection between solar activity and geomagnetic disturbances. A Norwegian physicist named Christian Birkeland conducted experiments showing that beams of electrons fired at a magnetic sphere created glowing patterns similar to auroras. He proposed that electrons from the sun were being guided by Earth's magnetic field, an idea that was largely correct but took decades to fully prove. Space-age technology transformed our understanding completely. Satellites launched in the 1960s and 70s could finally measure the magnetosphere directly, detecting the plasma flows, the magnetic reconnection events, the whole complex system that creates auroras. They could see the auroral ovals from above, watch them expand and contract in real time. Ground-based instruments improved too. Networks of all-sky cameras, magnetometers, radar systems that could track how energy flowed through the ionosphere. Now we can forecast auroras somewhat like we forecast weather. Satellites stationed between Earth and the Sun at a point called L1 watch for coronal mass ejections and fast solar wind streams. When they detect something heading our way, they send warnings, giving us anywhere from 15 minutes to a few days of advance notice, depending on what's coming. Scientists can predict how strong the geomagnetic storm might be, how far the auroral oval might expand, even what colors might dominate based on the energy levels involved. But predictions are never perfect. The aurora is too chaotic, too dependent on fine details of magnetic field orientation and solar wind turbulence. Often the forecasts give you a general probability, a sense that tonight might be active, but the actual display can surprise you. I've heard stories from people who traveled to the Arctic during supposedly quiet periods and saw incredible shows, and others who went during predicted storms and saw nothing but clouds. Part of the magic of aurora hunting is that element of chance, of patience, of just being there and hoping the sky decides to share its light with you. The best time to see auroras is during the equinoxes in March and September. This is when Earth's axis isn't tilted strongly toward or away from the sun, and for reasons related to how our magnetic field aligns with the solar wind, energy can flow into the magnetosphere more easily. Scientists call this the Russell-McPherson effect. There's something about the geometry during these months that favors magnetic reconnection, and statistically, more auroras happen and they tend to be more intense. But auroras can occur any time of year, any night really, if the conditions are right. They're most visible in winter simply because the nights are longer and darker in the Arctic regions. In summer, the sun barely sets at high latitudes, and even when it does, the sky doesn't get truly dark, so any aurora is washed out by twilight. The best viewing happens during those long polar nights, when darkness stretches for months, and the sky is a perfect black canvas waiting to be painted. Solar cycles also matter. The sun goes through an 11-year cycle of activity, from solar minimum when it's relatively quiet, to solar maximum when sunspots, flares, and coronal mass ejections are common. During solar maximum, auroras are more frequent and more likely to reach lower latitudes. During solar minimum, they still happen, but they're more confined to the far north and south, and major storms are rarer. We're always somewhere in the cycle, and tracking where we are helps predict general aurora activity over months and years. Some of the most powerful auroras ever recorded happened during what's called the Carrington event in 1859. A massive solar storm struck Earth, and auroras were seen as far south as Cuba and Hawaii. Telegraph systems, which were the cutting-edge technology of the time, went haywire. Operators reported sparks jumping for air equipment, papers catching fire, Some systems even continued to send messages after batteries were disconnected because the geomagnetic currents flowing through the ground were enough to power them. It was both amazing and frightening, a glimpse of how powerful space weather can be. If a storm like that happened today, the effects would be far more serious. Our modern world depends on technology that's vulnerable to electromagnetic pulses and geomagnetic currents. Satellites could be damaged or destroyed, cutting off communications, GPS navigation, weather forecasting. Power grids could fail as transformers overload from induced currents, potentially causing blackouts across entire continents that might take weeks or months to repair. Airlines would need to reroute flights away from the poles, where radiation levels spike and communication becomes unreliable. This is why space weather forecasting is so important now. It's not just about knowing when to go outside with a camera. It's about protecting infrastructure, giving power companies time to adjust their systems, warning satellite operators to switch to safe modes, ensuring that astronauts on the International Space Station take shelter in the most shielded modules. The aurora is beautiful, but it's also a visible sign of powerful forces that we need to respect and prepare for. Astronauts aboard the space station have a unique perspective on all of this. They orbit about 250 miles above Earth, which puts them right at the altitude where auroras occur. Sometimes they fly through the upper edges of auroral displays, surrounded by faint green glow, watching the structure ripple beneath them. From their vantage point, the aurora isn't above, it's below, draped across the planet like a luminous cloak. They can see the whole oval stretching for thousands of miles and watch how it responds to changes in solar wind in real time. Time-lapse videos taken from the station show auroras dancing over cities and oceans, moving in ways that seem almost alive. They pulse, they swirl, they race from one horizon to another. Against the black of space and the glow of city lights on the ground far below, the aurora creates this beautiful, layered view of Earth, part natural, part human, all connected. Astronauts describe it as one of the most breathtaking sights they witness during their missions, something that never gets old no matter how many times they see it. Auroras connect to other planets too. Earth isn't the only world with these lights. Any planet with a magnetic field and an atmosphere can theoretically have auroras, and we've found them throughout the solar system. Jupiter has the most powerful auroras in our neighborhood, driven by its immense magnetic field and its own rotation, which flings charged particles outward and then pulls them back toward the poles. Jupiter's auroras are so bright they can be seen with ultraviolet telescopes from Earth, glowing continuously at both poles. One of Jupiter's moons, Io, is volcanic, constantly spewing sulfur and oxygen into space. This material gets caught in Jupiter's magnetic field and creates a glowing footprint where Io's orbital path intersects with the planet's magnetic field lines. It's like Io is painting a spot on Jupiter's atmosphere as it orbits, a visible connection between moon and planet written in light. Saturn has auroras too, glowing blue and pulsing in time with radio emissions that the planet produces. Saturn's magnetic field is more aligned with its rotation than Jupiter's, creating more symmetric displays. The light comes primarily from hydrogen being excited, giving it that distinct blue hue. Spacecraft have captured images of these polar glows, delicate and beautiful, proving that auroral processes work on worlds very different from our own. Even planets without global magnetic fields have aurora-like lights. Mars, for instance, has patchy magnetic fields locked in its crust, remnants from a time billions of years ago when the planet had a global field. When solar wind particles strike these patchy magnetic patches, localized auroras flicker in the Martian sky, invisible to human eyes, but detectable by spacecraft instruments. They're scattered across the planet rather than forming rings, each one marking a place where ancient magnetism still persists. Venus shows faint glows on its night side when particularly strong bursts of solar wind strike its thick atmosphere. Without a magnetic field, these aren't true auroras in the traditional sense, but the underlying process is similar: charged particles colliding with atmospheric gases and causing them to emit light. Even the gas giants Uranus and Neptune have auroras, though theirs are strangely tilted and wandering because their magnetic fields don't align with their rotation axes. Their auroras move around the planet as the field spins, creating complex, shifting patterns. Beyond our solar system, astronomers have detected auroral emissions from brown dwarfs, objects that are too small to be stars, but too large to be planets. These failed stars generate powerful magnetic fields and produce radio bursts identical to those created by planetary auroras, suggesting they have glowing polar regions despite being essentially isolated in space. The process is universal. Wherever magnetic fields and charged particles meet, there's potential for light. Understanding auroras helps scientists think about exoplanets too. If we could detect auroral emissions from an exoplanet, it would tell us about its magnetic field, its atmosphere, maybe even its potential habitability. Magnetic fields protect atmospheres from being stripped away by stellar winds, just like it did to Mars billions of years ago. We'd lose our air, our water would evaporate, and Earth would become another dead rock orbiting the sun. The aurora is a beautiful side effect of the system that keeps us alive. There's something deeply moving about that realization. Every time you see the northern lights, you're seeing the shield that protects all life on Earth made visible. You're seeing proof that we're not separate from the cosmos, but connected to it, shaped by it, dependent on it. The same particles that create that gentle green glow are particles we need to be protected from, and the magnetic field that guides them into these beautiful patterns is the field that keeps them from reaching the ground in harmful quantities. In indigenous cultures, this connection was intuitive. They understood, without needing scientific instruments, that the aurora was part of something larger, something sacred. The Inuit stories about ancestors in the sky weren't wrong, not really. They were expressing the truth that we're connected to what came before, that the elements in our bodies were forged in stars that died long before the sun was born, and that we're still connected to those cosmic processes through the light that dances over the poles. Modern science gives us the mechanisms, the details of electrons and magnetic fields and atmospheric chemistry, but it doesn't diminish the wonder. If anything, understanding how the aurora works makes it more remarkable, not less. The fact that we can trace the path of a single particle from the sun's corona across 93 million miles of space through the tangled complexity of Earth's magnetosphere down into the atmosphere where it strikes an oxygen atom at just the right energy to produce that specific shade of green light, the fact that we can understand all of that and predict it and measure it, that's its own kind of magic. And yet, for all our understanding, the aurora still surprises us. Every display is different, shaped by countless variables that we can't fully track. The exact orientation of the solar wind's magnetic field, tiny fluctuations in the magnetosphere, variations in atmospheric density, all of these combine to create patterns that are never quite the same twice. You could spend a lifetime watching auroras and never see the same show repeated. This unpredictability is part of what draws people north. Aurora tourism has become significant in places like Iceland, northern Norway, Alaska, Canada's Yukon and Northwest Territories. People travel from all over the world, hoping for a chance to see the lights. They bundle up in extreme cold, venture out in the middle of the night, stand in darkness for hours, waiting. And when the aurora appears, when those first green ribbons start to glow on the horizon and then spread and dance across the sky, the wait feels worth it. I've heard stories from people who saw their first aurora and broke down crying. There's something about it that touches something deep, something primal. Maybe it's the scale, the reminder of how small we are beneath something so vast. Maybe it's the beauty, pure and natural, untouched by human hands. Maybe it's the silence, the way something so visually powerful can unfold without a sound, creating this strange disconnect between what you're seeing and what you're hearing. Or maybe it's the connection, the understanding that you're witnessing the universe in action, forces that existed long before you and will continue long after. For people who grow up in the Arctic, the relationship with auroras is different. They're not rare visitors, but familiar neighbors, part of the rhythm of winter life. Children grow up with stories about them, learning when to expect them, what shapes mean, how to read the sky. There's a casualness to it sometimes, locals glancing up, noting that it's a good aurora tonight, then going back to whatever they were doing. But even for them, there are nights when the display is so extraordinary that everyone stops, comes outside, just watches in silence. The aurora has inspired art across cultures and centuries. Painters have tried to capture its colors, though pigments never quite match the luminosity of the real thing. Photographers have built careers around chasing auroras, learning the technical skills needed to capture them, studying weather patterns and solar forecasts, traveling to remote locations again and again. The best aurora photographs are stunning, but even they can't fully convey the experience. They freeze a single moment, but they can't show you the motion, the way the light moves and breathes, the three-dimensional quality of curtains that seem to have depth even though they're just light in the air. Musicians have composed pieces inspired by the aurora too, trying to translate that visual movement into sound. There's this challenge in it, How do you capture something that moves in silence? Some composers use slow, ambient textures, long, sustained notes that shimmer and fade like the lights themselves. Others incorporate electronic elements, building layers of sound that pulse and shift, trying to mirror the way auroras can suddenly intensify or dissolve. Indigenous peoples created their own music around the aurora, songs that were meant to honor the lights or communicate with them, chants that carried the weight of generations of watching and wondering. Writers have struggled with it too, trying to find words adequate to describe what it's like to stand beneath the aurora. The vocabulary always seems insufficient. You end up reaching for metaphors, comparing it to curtains or waves or ribbons, but none of those quite fit because the aurora doesn't really resemble anything else in our experience. It's uniquely itself, and maybe that's why it keeps drawing us back, this thing that exists outside our normal categories of understanding. The aurora changes through the night in predictable ways if you know what to look for. Early evening, you might see quiet arcs forming along the horizon, subtle and still. As the night progresses toward magnetic midnight, that moment when your location rotates through the densest part of the magnetosphere's plasma sheet, activity typically increases. This is when substorms are most likely, when those explosive displays happen that can fill the entire sky. Then, in the hours before dawn, things often quiet again, the aurora retreating back to faint arcs or disappearing entirely as the magnetosphere stabilizes. But this pattern isn't rigid. Solar storms don't care about local midnight. A massive burst of solar wind can hit at any time, creating auroras at unusual hours, pushing them farther south than they normally reach. There've been auroras visible from Scotland, from northern United States, even occasionally from places as far south as the Mediterranean during extreme events. When this happens, people who've never seen auroras before suddenly find their night sky filled with color, and the experience can be disorienting, almost frightening if you don't know what you're looking at. Historical records contain descriptions of these rare low-latitude auroras, and they're often tinged with fear. Red auroras especially were seen as omens, signs of coming war or disaster or divine anger. In 1859, during the Carrington event, newspapers reported widespread panic as red lights appeared in skies where they'd never been seen before. Telegrapher operators thought their buildings were on fire, rushing outside to find no flames, just the sky itself glowing. People gathered in streets, unsure whether to be awed or terrified, and in the absence of scientific understanding, many leaned towards terror. We know better now, but there's still something unsettling about seeing auroras where they shouldn't be. It's a reminder of how powerful the sun can be, how much energy it can release, and how vulnerable our technology-dependent civilization is to space weather. A Carrington-class event today would be catastrophic in ways the Victorians couldn't have imagined. Estimates suggest it could cause trillions of dollars in damage, knocking out power grids across continents, destroying satellites that we rely on for everything from communication to navigation to banking. It would take years to fully recover. And it's not a question of if such an event will happen again, but when. The sun is a star, and stars have storms. We've been lucky that in the century and a half since Carrington, we haven't experienced another storm quite that severe, but we've had close calls. In 2012, a massive coronal mass ejection erupted from the sun, one that scientists later said would have been as powerful as Carrington, maybe more so. It missed Earth by about a week in orbital position. If it had erupted just days earlier when that region of the sun was facing us, we would have been hit, and the modern world would have faced its first true test against extreme space weather. The aurora, then, is both beautiful and a warning. It's a visible manifestation of the sun's power, a constant reminder that we live in a dynamic solar system where energy flows and storms rage, and our little planet sits in the middle of it all, protected by a magnetic shield that we often take for granted. When you see particularly strong auroras, when they're bright enough to cast shadows on the snow, when they're red instead of green, when they extend far beyond their normal range, those are the times when the magnetosphere is under stress, when the shield is working hard to protect us. Scientists monitor this constantly now. There are networks of ground-based magnetometers spread across the Arctic, measuring subtle variations in Earth's magnetic field that indicate auroral activity. All-sky cameras at stations throughout the North capture images every few seconds, creating continuous records of how auroras evolve. Satellites in various orbits measure different aspects of the system, some watching the sun for outbursts, others tracking the solar wind as it flows past, still others positioned to observe the magnetosphere itself and how it responds to incoming energy. All of this data feeds into models that try to predict space weather. It's similar to atmospheric weather forecasting in some ways, but more challenging because we have far fewer measurements to work with, and the system is more chaotic. Predicting whether there will be an aurora tonight is relatively straightforward if you know the solar wind conditions. Predicting exactly how bright it will be, what colors will dominate, how long it will last, those details are much harder. The magnetosphere is sensitive to tiny variations that we can't always detect in advance. Still, the forecasts have gotten remarkably good. Websites and apps now provide aurora alerts, giving people advance notice when conditions look favorable. Photographers and tour operators plan their nights around these forecasts. Indigenous communities in the Arctic sometimes use them too, though many rely just as much on traditional knowledge, reading signs in the weather and the season that have predicted auroras for generations. The color of an aurora can tell you stories about what's happening in the atmosphere, if you know how to read it. That common green, glowing at around 100 kilometers altitude, that's your baseline, indicating moderate energy electrons hitting oxygen atoms. If you start seeing red above the green, that means higher energy particles are penetrating to greater altitudes where the air is thinner. Red auroras can extend up to 400 kilometers or more, way up at the edge of space where satellites orbit. Blue and purple at the lower edges mean nitrogen is being excited, and that usually indicates particularly energetic particles reaching lower altitudes where the air is denser. These colors often appear during the most active phases of a display, racing along the bottom of curtains as they move. The combination of colors creates this layered effect, greens and reds and purples all stacked vertically, each one marking a different altitude and a different atmospheric component responding to the incoming energy. Sometimes you'll see auroras that are almost entirely red, especially during very intense storms when high-energy particles penetrate deep into the atmosphere. These red auroras can be dimmer than the green ones because human eyes aren't as sensitive to red light in darkness, but cameras pick them up beautifully. They spread across huge areas of sky, soft and diffuse, like the atmosphere itself is blushing. Ancient observers who saw these would have been truly frightened because the entire dome of the sky would take on this eerie crimson glow, nothing like the normal greens. The speed at which auroras move is fascinating too. When you see a curtain of light race across the sky, it's not actually the light moving, not really. It's a wave of particle precipitation moving through the atmosphere, exciting atoms along its path. Each point of light exists for fractions of a second before fading, but new points are continuously lighting up in sequence, creating the illusion of motion. It's similar to how a wave in a stadium works. Individual people standing and sitting, but the wave itself travels smoothly around. These waves can move incredibly fast, the apparent motion reaching thousands of kilometers per hour. Your eyes can barely track them, just catching glimpses of structure racing overhead before it's gone. High-speed cameras reveal that the aurora is even more dynamic than we perceive, with structures forming and dissolving on timescales of seconds or less. There's always more happening than we can consciously process, layers of detail that our brains smooth over to create a coherent image. Pulsating auroras are different. They're more subtle but hypnotic in their own way. These appear as patches of light that brighten and fade rhythmically, on and off, sometimes for hours. The pulsing is caused by waves in the magnetosphere, electromagnetic oscillations that periodically allow electrons to precipitate into the atmosphere. When the wave peaks, particles flow through and the patch brightens. When it dips, the flow cuts off and the patch dims. The rhythm can be very regular, like a heartbeat, or more irregular, creating complex patterns of flicker. Watching pulsating aurora is almost meditative. There's something about that steady rhythm that draws you in, slows your breathing, quiets your mind. People report losing track of time while watching these displays, standing in the cold for much longer than they intended because they couldn't look away from the pulse. It's like the sky is breathing, and you find yourself breathing with it, syncing up to this cosmic rhythm without even realizing you're doing it. Black auroras are among the strangest phenomena, and they weren't really understood until recently. These appear as dark bands or patches within bright auroral displays, regions where the light seems to be absent even though it's all around them. For a long time, scientists weren't sure what caused them. They're not shadows, there's nothing blocking the light. Instead, they're regions where electric fields have formed that actually prevent electrons from reaching the atmosphere. The charged particles are being deflected away, creating these voids in the glow. Seeing a black aurora is eerie because it feels wrong somehow, like the sky has holes in it, dark rivers flowing through the light, moving and changing shape, anti-auroras made of absence rather than presence. They're most common during the recovery phase after a substorm, when the magnetosphere is reorganizing itself and electric fields are establishing new patterns. They mark boundaries, transitions between different regions of plasma flow. Then there's Steve, which we talked about earlier, but it's worth coming back to because it represents something important about scientific discovery. Steve was found not by professional researchers in labs, but by amateur aurora photographers who noticed something odd in their images and started comparing notes online. They called it Steve initially as a joke, a reference to a children's movie. But when scientists investigated, they realized it was a genuinely new phenomenon, something that didn't fit existing models of auroral physics. This kind of citizen science is becoming more common. There are thousands of people around the world now with good cameras and an interest in auroras, taking photos every clear night, sharing them, discussing them. Collectively, they're generating more observations of auroral phenomena than any research program could possibly manage. And occasionally, they spot patterns that professionals have missed, like Steve, or unusual behaviors, or rare configurations that happen too infrequently to show up in formal studies. The green picket fence that sometimes appears beneath Steve is another citizen science discovery. Photographers noticed these regular, vertical columns of green light flickering rapidly under the purple arc, and scientists are still working out exactly what causes them. The current theory involves waves propagating through the ionosphere, creating these periodic structures, but the details are still being refined. It's a reminder that even with all our satellites and instruments, there's still much we don't fully understand about Earth's magnetic environment. Understanding auroras requires understanding the whole system, from the sun's core, where the energy originates, through the corona, where it's released, across interplanetary space, where it propagates, into Earth's magnetosphere, where it's processed and stored, and finally into the atmosphere, where it becomes visible. Every part of this chain involves complex physics, and they're all coupled together, each affecting the others in ways that create feedback loops and nonlinear responses. The sun's activity cycle, that 11-year period from minimum to maximum and back, is driven by a magnetic dynamo deep inside the star. Magnetic fields are generated by the motion of conducting plasma, and they rise through the sun's layers, eventually breaking through the surface as sunspots and active regions. These are the sources of solar flares and coronal mass ejections, the eruptions that send plasma and magnetic field streaming outward. When a coronal mass ejection occurs, it's like the sun exhales a chunk of its own atmosphere into space. Billions of tons of plasma, threaded with magnetic field, expanding outward at speeds that can reach several million miles per hour. As it travels, it maintains its own internal magnetic structure, a frozen-in field that will interact with Earth's field when they meet. The key moment happens at the boundary of Earth's magnetosphere, called the magnetopause. This is where the solar wind, or in this case the coronal mass ejection, first encounters significant resistance from Earth's magnetic field. The interaction depends critically on the orientation of the incoming magnetic field. If it's aligned with Earth's field, pointing north, the two fields tend to reinforce each other and not much happens. But if the incoming field points south, opposite to Earth's field, they can reconnect. Magnetic reconnection is one of the most important processes in space physics, and it's surprisingly difficult to explain intuitively because it involves magnetic fields changing their topology, which isn't something we experience in everyday life. Essentially, field lines from the sun and field lines from Earth join together, forming new connections, and in the process, magnetic energy is converted to kinetic energy, accelerating particles to high speeds. When this happens at the magnetopause, it opens a door. Energy and particles from the solar wind can flow into the magnetosphere, filling it with plasma that gets stretched back into the magnetic tail on the night side. This is the loading phase, energy being stored like pulling back a rubber band. The tail can extend back for millions of kilometers, far past the moon's orbit, and inside it, magnetic field lines are stretched thin and stressed. Eventually, the stress becomes too much, and reconnection happens in the tail too. Field lines snap back to a more relaxed configuration, and the stored energy is released explosively. Particles that were trapped in the tail are suddenly accelerated, flung back to Earth along magnetic field lines that guide them to the poles. This is the substorm we talked about, and it's what causes the aurora to suddenly intensify and become active. The beauty of the aurora is that it makes all this invisible physics visible. Every bright curtain, every racing arc, every pulse of color is a direct visual representation of these magnetic processes playing out in space around us. You're not just seeing pretty lights, you're seeing magnetic reconnection, you're seeing particle acceleration, you're seeing the magnetosphere breathing and adjusting to the pressure of the solar wind. The aurora is a diagnostic tool, a natural display that reveals the state of Earth's space environment. This is why scientists study auroras so intensely. They're not just interested in the lights themselves, they're using the aurora to understand fundamental processes that occur throughout the universe. Magnetic reconnection happens in the sun's atmosphere, creating solar flares. It happens in the magnetospheres of other planets. It happens in the disks around black holes, powering jets that shoot out for thousands of light years. It happens in the magnetic fields of galaxies, in the thin plasma between stars. Understanding how it works here, in Earth's magnetosphere, where we can measure it in detail, helps us understand these far more distant and energetic phenomena. The same is true for the other processes involved: particle acceleration, wave-particle interactions, plasma instabilities, magnetic turbulence. These are universal phenomena, and Earth's magnetosphere is essentially a natural laboratory where we can study them in situ. Every aurora teaches us something not just about Earth, but about how the universe works at fundamental levels. And there's still much we don't know. For all our satellites and models, we still can't predict exactly when a substorm will occur or how intense it will be. We can't always predict when auroras will happen at specific locations. We don't fully understand all the mechanisms that accelerate particles to the energies needed to create auroras, particularly the very high-energy particles that create red emissions. There are types of auroral displays whose physical causes are still debated. Steve opened up entirely new questions about plasma flows and atmospheric heating. This means that aurora research is ongoing, active, constantly evolving. New satellites are launched with better instruments. New ground-based observatories are built at strategic locations. Computer models become more sophisticated, able to simulate the magnetosphere in greater detail. And every so often, nature surprises us with something unexpected, some configuration we hadn't predicted, some behavior that doesn't fit our models, and we have to go back and refine our understanding. The aurora connects to climate science too, in ways that are subtle but important. Energy deposited into the upper atmosphere by auroras affects its temperature and composition. During major geomagnetic storms, enough energy can flow into the thermosphere to heat it significantly, causing it to expand. This expansion increases atmospheric drag on satellites in low Earth orbit, causing them to slow down and lose altitude. The effect is measurable and can be substantial. Satellites can lose kilometers of altitude during strong storms. The aurora also creates nitrogen oxides through the chemical reactions that occur when energetic particles break apart molecules. These nitrogen oxides can gradually drift down through the atmosphere, eventually reaching the stratosphere where they affect ozone chemistry. The amounts are small compared to human-produced pollutants, but they're part of the natural system, a connection between space weather and atmospheric chemistry that needs to be included in complete climate models. Some researchers have even suggested that variations in auroral activity might have subtle effects on cloud formation or atmospheric circulation, though these ideas are still being investigated and are controversial. The challenge is that the effects are small and intermittent, hard to separate from all the other factors that influence weather and climate. But the possibility that space weather could influence surface weather, even slightly, is fascinating and suggests connections we're only beginning to explore. The aurora also affects radio communications, and this has been important from the early days of radio. The ionosphere, where auroras occur, is also where radio waves are reflected, allowing long-distance communication. When auroras are active, they disturb the ionosphere, creating irregularities and structures that can scatter or absorb radio waves. This was a major problem for military communications during the Cold War, and it remains an issue for amateur radio operators, pilots, and anyone else relying on high-frequency radio. GPS navigation can also be affected. The signals from GPS satellites pass through the ionosphere on their way to receivers on the ground, and ionospheric disturbances can delay these signals or cause them to scatter. During strong geomagnetic storms, GPS accuracy can degrade, sometimes significantly. This matters for applications that require precise positioning, things like precision agriculture, surveying, aircraft navigation, even timing systems used by financial networks that rely on GPS clocks. Modern technology has made us more vulnerable to space weather in some ways, even as it's made us more aware of it. We depend on systems, satellites, power grids, communications networks that are all potentially affected by the same solar storms that create beautiful auroras. This creates an interesting tension between appreciating the beauty and recognizing the risk. The aurora is both gift and warning. Indigenous knowledge about auroras often included practical elements alongside the spiritual. People living in the Arctic had to be attuned to their environment in ways that modern people often aren't. They noticed patterns like auroras being more common in certain seasons, or particular types of auroras being associated with particular weather conditions. Some of this traditional knowledge is being revisited by scientists now, looking for patterns that might have been overlooked. There are stories, for instance, about auroras affecting animal behavior. Reindeer supposedly become nervous when strong auroras appear, and there are reports of dogs howling or birds becoming restless. Whether this is a response to the light itself or to subtle electromagnetic effects or something else entirely isn't clear. Animals have senses we don't, and it's possible they detect aspects of auroral activity that humans miss. Research into this is limited but intriguing. The experience of seeing your first aurora is something people often remember their entire lives. There's a quality to it that photographs can't capture, a presence, a sense of scale and movement and color that has to be experienced directly. People describe feeling small beneath it, humbled but also connected, part of something much larger. There's often an emotional response, tears, laughter, awe that goes beyond rational explanation. Part of it might be the unexpectedness. Even if you travel north hoping to see auroras, even if you know intellectually what they are, when they actually appear and start moving across the sky above you, the reality exceeds imagination. Your brain hasn't evolved to process something like this. There's no survival reason to have developed responses to moving lights in the sky, so it hits you fresh, without the filters we apply to more familiar experiences. The cold adds to it too. Experiencing auroras almost always means standing outside in winter Arctic temperatures, and there's something about that combination, the physical discomfort of the cold, the darkness, the silence, and then this explosion of color and movement overhead. Your body is telling you to go inside, to seek warmth, but your eyes won't let you look away. You end up standing there long past when you're comfortable, watching until the display finally ends, or you literally can't feel your fingers anymore. Photography has changed how people experience auroras in recent years. With modern cameras and sensitive sensors, you can capture auroras in ways that weren't possible before, bringing out colors and details invisible to the naked eye. This has created a sort of parallel aurora, the photographed one that appears on screens and in galleries, sometimes more vivid and dramatic than what you see with your eyes in the moment. There's debate in the aurora photography community about how much processing is appropriate. Some argue for showing the scene as realistically as possible, reflecting what a person would actually see. Others push the processing further, stretching colors, enhancing contrast, creating images that are beautiful but perhaps not entirely accurate. Neither approach is wrong, they're just different ways of sharing the experience, one emphasizing fidelity, the other emphasizing impact. Time-lapse photography has revealed aspects of auroral motion that are hard to appreciate in real time. When hours of aurora are compressed into minutes of video, you can see patterns emerge, waves moving across the sky, structures forming and dissolving, the whole display breathing with a rhythm that's only apparent when time is accelerated. These time lapses have become popular on social media, introducing millions of people to auroras who might never travel north to see them in person. Virtual reality experiences of auroras are being developed too, trying to capture something of what it's like to stand beneath them. With 360-degree video and spatial audio, you can create immersive environments that simulate being in the Arctic under active auroras. It's not the same as being there. You can't replicate the cold or the darkness or the sense of isolation, but it's another way to share the experience with people who can't make the journey themselves. Education about auroras has expanded enormously with the internet. Websites, apps, social media accounts dedicated to aurora forecasting and photography have created communities of enthusiasts, sharing information, helping each other, celebrating successful mites. The knowledge that used to be held by scientists and locals is now accessible to anyone with an internet connection. You can learn about solar wind conditions, magnetosphere dynamics, how to read forecasts, where to go, when to go, all before you ever leave home. This democratization of knowledge has its benefits and challenges. More people are aware of auroras now. More people travel to see them, which supports local economies in Arctic regions, but also creates challenges for fragile environments and small communities suddenly seeing tourism influxes. There's a balance to be found between sharing these wonders and protecting them, though auroras themselves are obviously not harmed by being watched. Some of the best aurora viewing locations have become famous. Tromsø in Norway, Fairbanks in Alaska, Yellowknife in Canada, Abisko in Sweden, Reykjavik in Iceland. These places see thousands of aurora tourists every winter. They've built infrastructure around it, lodges and tours and viewing platforms, entire local economies driven by people wanting to see the lights. On any given clear night during aurora season, you'll find crowds gathered outside these towns, cameras on tripods, people bundled in extreme cold weather gear, watching the sky. But you don't need to go to these famous locations. Anywhere within or near the auroral oval gives you chances to see them. Some of the most memorable aurora experiences happen in remote places, far from any infrastructure, where you're truly alone under the sky. The silence is deeper there, the darkness more complete, and when the aurora appears, it feels like it's performing just for you. There's also something to be said for seeing auroras from places where they're less common. When they extend south during major storms, people at lower latitudes get to experience them against familiar landscapes, over their own homes and cities. The contrast between the ordinary and the extraordinary, seeing something so otherworldly in your own backyard, can be just as powerful as traveling north to find them. The future of aurora science involves better prediction, more sophisticated modeling, and possibly even ways to influence the magnetosphere, though that last idea is purely theoretical at this stage. As we expand into space, establishing permanent bases on the Moon or eventually Mars, understanding space weather becomes crucial. Astronauts outside Earth's protective magnetosphere are much more vulnerable to radiation from solar storms, and predicting these storms accurately could literally be life-saving. There's also interest in artificial auroras, plasma released into the upper atmosphere from rockets to study auroral processes in controlled ways. These experiments create small, temporary glows that help scientists test theories about how particles interact with the ionosphere. They're tiny compared to natural auroras, visible only to sensitive instruments, but they provide valuable data that can't be obtained any other way. Looking further ahead, some have speculated about whether other intelligent species on other planets might have auroras, and whether those lights might have played a similar role in their development, inspiring wonder and curiosity, driving scientific inquiry. If a planet has a magnetic field and an active star, it probably has auroras, and if there's life there capable of seeing them, they might have looked up and wondered just as we do. It's a pleasing thought that across the galaxy, maybe across the universe, beings of different types might all share this one experience of watching their skies glow with color. The aurora reminds us of our place in the cosmos in concrete, visible ways. It's easy to feel disconnected from space, to think of it as this abstract realm that doesn't affect our daily lives. But the aurora proves otherwise. It shows us that space isn't empty and separate. It's full of energy and particles and fields, and we're immersed in it, protected by a magnetic shield that we only notice when the particles it deflects light up our sky. We're part of this system, not observers outside it. Every element in your body was forged in stars, scattered into space when those stars died, eventually coalescing into the solar system and Earth, and eventually you. The oxygen atoms in your lungs are the same type that glow green in the aurora. The iron in your blood is related to the iron in Earth's core that creates the magnetic field that guides those auroral displays. The electrons flowing through your neurons as you think about this are fundamentally the same electrons streaming from the sun. We're made of the same stuff that makes the aurora, just arranged differently, briefly conscious, able to look up and recognize the connection. This perspective, understanding that we're not separate from the universe, but made of it and part of it, is maybe the deepest gift that studying auroras offers. It changes how you see yourself, how you see Earth, how you see the sun and stars. Everything is connected through these fundamental physical processes that play out across all scales, from the quantum interactions that create each photon of light to the galaxy-scale magnetic fields that structure the cosmos. When you watch an aurora, you're watching the universe doing what it does: energy flowing, fields interacting, matter responding. It happens to create beauty that we can perceive, but it would happen whether we were here or not. The aurora doesn't exist for us. It exists because the universe works in certain ways. We're just fortunate enough to exist in a place and time that we can see it, understand it, appreciate it. And maybe that appreciation, that wonder, maybe that's a meaningful part of the universe too. We're the universe becoming aware of itself, at least in this tiny corner of it, and the aurora is one of the ways that awareness manifests, one of the places where the deep physics of reality becomes something we can directly experience. So, when you see the northern lights, remember that you're not just watching a light show. You're watching the sun breathe. You're watching Earth respond. You're watching billions of years of cosmic evolution that led to this moment, this planet, this magnetic field, this atmosphere. You, standing there able to see and understand it all. You're watching proof that we're connected to the cosmos in intimate, direct, physical ways. And in that moment, under those moving lights, in that deep cold and deeper silence, you might feel something shift in your perspective. The concerns that seemed important might suddenly feel smaller. The boundaries you draw between yourself and the world might blur. You might feel, just for a moment, like you're exactly where you're supposed to be, part of something vast and ancient and ongoing, something that was here before you and will continue after you. And somehow, that's not frightening, but comforting. The aurora has been doing this to people for as long as people have existed. It's been inspiring wonder, prompting questions, making us think about forces beyond our direct control, connecting us to the sky and the sun and the earth beneath our feet. The science we've developed to explain it doesn't diminish any of that. It enhances it, gives us new layers of meaning to add to the old ones. The ancestor who saw the aurora as spirits dancing was seeing the same thing we see when we understand it as electrons and magnetic fields. Both perspectives are valid. Both are true in their own ways. As you drift towards sleep now, imagine yourself standing under those lights one more time. Feel the cold air on your face. See your breath turning to mist. The stars are brilliant overhead, harder and clearer than you've ever seen them. And then, along the northern horizon, a faint green glow begins to appear. It brightens slowly, extending upward, forming an arc that stretches from east to west. You watch as it intensifies, as structure begins to appear within it, folds and curtains rippling gently. The arc breaks apart into ribbons that twist and curl, and suddenly they're moving, racing across the sky overhead. Colors shift and blend, green dominating with hints of purple at the edges, maybe a touch of red high above. The motion is hypnotic, endless variations, never repeating, each moment new. You stand there, watching, time becoming meaningless, cold forgotten, aware only of the light and the silence and the vast dark sky. And somewhere in that moment, you understand something without words. You understand connection. You understand that you're standing on a planet that's hurtling through space at thousands of miles per hour, protected by an invisible field generated by molten metal deep underground, being bombarded by particles from a nuclear furnace 93 million miles away. And all of this creates the beauty flowing across the sky above you. You understand that you're made of stardust, literally, and the light you're watching is also stardust. Energy and matter dancing together in the way they've danced for billions of years. You understand that this will continue long after you're gone. The sun will keep sending its wind. Earth will keep its magnetic shield. The aurora will keep glowing over the poles. And maybe someday, someone else will stand where you're standing, feeling what you're feeling, part of the same long chain of consciousness, reaching back through time, forward into the future. All of us looking up, all of us wondering, all of us connected through this shared experience of witnessing the universe reveal itself. Let that thought comfort you as you sink deeper towards sleep. You're part of something vast, something ancient, something beautiful. The same forces that create the aurora flow through you, the same elements, the same energy, just temporarily arranged into the form that is you, briefly aware, lucky enough to know what you're part of. And that's enough. That's more than enough. The lights continue to move in your imagination, swaying gently now, slower, softer. The colors fade from bright to pale. The motion stills. The arc retreats back towards the horizon, dimming, until finally there's just darkness and stars and the deep, cold peace of an Arctic night. Your breathing has slowed without you noticing. Your body is heavy, relaxed, warm despite the imagined cold. The aurora has done what it always does, connected you to something larger, reminded you of beauty and mystery and the strange, wonderful universe we find ourselves in. And now it's time to rest, to let those thoughts drift away like the lights drifting back below the horizon, to sink into sleep with the memory of color and motion still glowing softly behind your eyes. So, if you found some peace in this journey through the science of the aurora, if these quiet revelations helped you relax and drift, you might want to explore more stories like this, more gentle science that helps you unwind and find sleep naturally. Thank you for spending this time with me. Let me know in the comments where you're watching from and what time it is for you right now. I love hearing from all of you. This is Aurora signing off from the Late Night Science Channel. Sleep well, fellow traveler, wherever and whenever.